life. So we'll talk about life, because the true revolution, which, yeah, I'll still 1 more minute that I promised. So the true revolution which happened in this respect, which I'm telling information here, it's in biology. Physics is kind of still, this revolution is still happening, and in biology it's already full swing. So let's talk about life. And this lecture will be maybe the next one. What do we need for life? Each one of us to survive. What we need? Eat, drink, right? So we need energy and matter. But can we say that we consume energy or matter? Can one consume energy?
Sort of indirectly. I guess it depends on what you mean by consume.
I mean that you've got something and then left something, but something remains with you forever, or at least for now. Okay? So, of course, if you grow, you do consume matter. You build yourself, you're getting larger and larger and larger. Right? Then you are my age, you're getting smaller, actually. Okay? But at least when you are kind of a normal adult, you more or less have the same number of atoms in you, which means that you do put matter in your mouth every day, right? But then this matter also goes out, and it's basically the same atoms. Well, it could be different atoms, but of the same elements. And also, no matter how many things you eat, the energy is conserved, right? So you do not store energy in you, right? You emit this energy as a body heat, most of it. So we do not consume energy, we just get some energy and get it out. So we just on a flow of energy, there's flow of energy through us. And there is flow of matter through us. The matter comes into us and the matter comes out. Looking at atoms, the same atoms, just differently arranged, right? So what do we consume? To live. What is needed to live? Okay, let's define what is to live. So look at me. This is a set of atoms, right? So what differentiates this set of atoms of another set of the same atoms, which we can say, no, this is not a living person. This set of atoms is a living person, and this set of atoms is not a living person. Yes?
Emergent complexity?
Yes. We are a very improbable combination of atoms, very much. If we let our atoms to be in a state of maximal entropy, namely most probable state, that would be dead body, long decayed after death. That would, our atoms would really return to their most probable thermal equilibrium. So we are in a very, very improbable state, and we want to stay in this very improbable state. A natural tendency of our atoms, of any physical system, is to go towards more probable state, towards increasing entropy. But we want to go there. We don't want to increase entropy inside us. Okay? So when we eat and drink and consume energy and mass, we actually try to not increase our entropy, to stay the way we are. Which means that we somehow need to get this excess of entropy out. So when you think about what we are really doing, and that's a moment when there's revolution in biology happened, and it's now happening like non-stop. There is a famous saying by Dawkins that inside every living being, not a spark of life, it's a bit of information. Okay? Technically, our way of preserving our unique, very improbable state is replication. We always try to replicate our proteins, all this stuff. But on the other hand, to do it, we need energy. But we get it energy and we throw it away. What's the difference between energy and matter that we get? For example, you take a piece of chocolate. You know how many calories in 100 grams of chocolate? Scary, I mean, 500. Okay. Imagine how much information processing went into packing 500 calories into a small bit of matter. Nature does not do it. It's really, some people worked to make us fat and packed all this. On the other hand, what comes out of us, a body heat, what our excretionary system sends out, it's a very, very disordered energy and a very, very disordered matter. So what every living being does, it intercepts the flow of energy and matter from a low entropy sources to high entropy sinks. In this way, what we obtain is ordered, and it allows us to sustain our order. And what goes out is disordered, more disordered than what comes in, and then it allows us to throw away this excess of entropy, which literally means that we consume information. And plants, where plants get their energy? Well, you know where, from sun, right? Is sun a low entropy source of energy? Yes?
Somewhat low entropy because it's a very high temperature, so it emits a lot of energy with low entropy with it.
Absolutely. It's a very correct question. And I once was given on TV some kind of a popular interview or lecture, and then somebody after that wrote that after your lecture I've realized that indeed sun is a very low entropy source of energy, and it changed my life. It was very, very touching. So let's write now more or less Carnot type formula, which tells us how much energy we need to get information or to make an entropy change. So again, what we are doing, I just want to take this old Carnot picture from which I guess we started the first lecture, right? So I'll have a reservoir with T1, which gives me how I call it, Q. It gives me Q, and then some work goes out, and then there is a reservoir T2, right? And so what this get me? Delta, this get me Q over T1. This is entropy over here. And this is Q minus W over T2. That's entropy which goes it. And so I get, so this is S1. This is S2. And I am interested in delta S, which is S2 minus S1, which is Q minus W over T2 minus Q over T1. But now I want to turn tables and ask how much Q I need to get this delta. This is the amount of information, right? Or this is how much entropy I have thrown away. So you may write that the Q is, not surprisingly, T delta S plus W if you did work, and 1 minus T2 over T1. And again, as now not for thermal engine for which we were turning heat into work, but now for producing that amount of information, we see how it's getting ineffective when T1 going to T2. when T1 going to T2, so we are working with a very close in their temperature sources. You are plants, right? So you get this Q out, and plants also emit body heat, right? So when T1 is close to T2, this is a very small, this is very large. So for every bit of information, you need a lot of heat. On the other hand, when your T1 goes to infinity, which is sun, it just disappears. It does not matter how hot is sun, as long as it is much hotter. Okay, and if you don't do work, this is just T delta S. Okay, so this is a simple formula. So sun is indeed a very low entropy source. And now you can also ask to turn it around and say, we know more or less how much heat our body generates, right? Approximately, well, if you're lazy, if you are mid-size human, it's about 300 watts. And the temperature is 300 Kelvin, let's say, okay. And K is one, well, actually it's 200 more for, this is for a big person. And the K is 1.32, 10 minus 23. And so on. If you look at delta S, it will be now dimensionless. You take Q divided by T times K, you get of order 10 to 23 bits per second. That's what more or less, if we don't do work, it's just all the processes in our body, this requires a lot of processing information. That's how much bits we typically process. But now it's interesting to discuss how actually this information is processed. So the moment that we realized that all in our life is about processing information, and energy and matter are just tools. At 50s, people started doing experiments when people guessed, not guessed, just recognized objects. So you sit looking at a screen, and on the screen there are numbers which appear. And then you say 5, and then you say, okay, 8. So you just name the number, and they measure how much time you need before you answer. Okay? And so you can make experiment where you say, okay, so now will be numbers between 0 and 10. Then another experiment will be numbers between 0 and 100. Then will be numbers between 0 and 1,000. How you would expect time reaction depend on the n, on the interval of numbers. It's, by the way, experiment which you can do at home. Well, you need some kind of control, etc. Because people are very good at fooling themselves. So how would you expect this dependence? Guess. It's a very simple experiment. One of the most remarkable discoveries of the previous century. It's yes.
Constant plus something linear, the logarithm of the number of choices.
The number of choices is n, and for large n, constant does not matter. So the right answer is, of course, it's a logarithm of n. You have a menu, and in this menu you need to find an item. If this menu is structured, whatever, alphabetically, it could be a phone book, or restaurant menu where you have appetizers, entries, desserts, etc. It's log. When your list is unordered, it's linear with n. Logarithm always tell you that you make a hierarchical decision. Well, log comes, right? You say right or left. You know, first third of the menu, second third or third third, right? Is it among appetizer, etc. And then it's ordered according to price, for example, etc. So logarithm tells you that the people were doing with an ordered somehow. And so the decision when you choose which one actually this is a recognition process, right? So you need to take something out of your memory and recognize it over there. And then people did a little bit more interesting things. They were starting to show these numbers with different frequencies. So they were numbers from 1 I n, but they have different frequencies, different probabilities, pi, pn. The sum was unity, but some were kind of more frequently appearing than others. What would you expect the reaction time to be? I'm trying to make a discovery together with you, right? You're graduate students, you are researchers, right? So I want to show you how you actually, because before you make discovery, you imagine it, right? So why would they do this experiment? Why would they start changing frequency? What was they expecting?
There won't be entropy.
Of course. The time now was from Boltzmann to Gibbs. Okay? So this was early 50s, and people were just learned from Shannon information theory and all that stuff. They were very excited, and they started to apply it everywhere. Okay, but now they also started to do something more non-trivial. They started to make these letters or numbers correlated, namely that there was some kind of a p of I j, okay, or there was some kind of a general p of I j correlation thing, okay, and then what they were doing were also a different thing. They were not prescribing these probabilities, and they were prescribing reaction time. And that was the most beautiful experiment out of it. So they say some symbol appears, and after, let's say, 2 seconds, a signal tells you to give an answer, right? Or just boom, and you need to give an answer. So when people give an answer in a prescribed time, so time now is given, they start making errors. The moment they are making errors, appears a non-trivial probability distribution. So now people not recognize for every j that this is j. They sometimes can tell that this is I, because they making errors. Okay? So now what you can do, you can now compute this. This is something that you measure. This is something that you prescribe. Okay? Again, now the question is, how out of these numbers you can compute this? What quantity built out of our probability distributions would be proportional to the reaction time? So we have a set of inputs, which are what appears on a screen. We have a set of outputs. It's what is people recognize and give. There is some kind of a non-trivial remaining entropy over there, which means that they are kind of related, but and you can change this time, and you ask what is it out of the statistics that you can compute, which would be linearly proportional to this time. So what is your guess? This was just S, and this is S. Just an entropy of your signal, right? But this is assuming that you really every time give a right answer, right? So in this case, the time was like this. Now they kind of imagine that they made a shorter time. So you start making errors, right? So your time is now less than this because you're making errors and there is still a remaining entropy even after you've given an answer. So what must be this proportional to? Yes, mutual information. So what would be here is S of j minus S of j of k. Okay? This is indeed was experimentally measured. So people actually went there. So what they did, they measured this. Just every event is some I and j. Sometimes they coincide, sometimes they do not coincide. So you can measure this. Then you can get p of I just summing over j p of I and j. Okay. You can do this. Then you can do conditional averaging, and then you can compute this. So out of this, you compute this, and then you take this, divide by z, and you get conditional, and you compute conditional. In miracle, it was proportional. So not only the statistic of course it takes time. It's a very long experiment because when you initially start answering, you don't know. So what our brain actually does, it statistically processes this information, and after a while, it establishes this response time, which is more or less proportional, directly proportional, linearly, to the entropy of expected distribution, right? Which is and this entropy is not necessarily Boltzmann entropy. It could be a much more complicated thing. So actually, our brain recognizes the different frequency and also recognizes correlation between neighboring signals. Okay? This is really something which tells that what we learn has a direct relation. So it's not just an abstract categories. But now let's look a little bit under the hood, how it works inside. And I want you play God Almighty and design a response system. So imagine that you have some kind of a signal, and we'll call it X, and this is the signal. Some, Y. How I actually call it X or Y, I want to be consistent because I really want to have a response. And let's say for simplicity, I would have my signals weak, medium, and strong. Okay? And now my response would be just a number of signals that my neurons, let's say this is an eye or ear, it gets something which is intensity, contrast, whatever. And so I need to kind of get here kind of 3 different types of response, but I need to choose a response curve, a response function, right? So I can just take it like this. And I am in this interval. So the interval is fixed, right? And here the interval is fixed. I just need to divide this interval according to this, right? What will be actually will be signal. So I can just take it linearly, which means that as long as this is in this will be sending this type of signal. As long as this will be the same, and this will be exactly the same. But I can do it differently. I can say, I don't much care about weak signals. This is not really important. I can choose a curve which is like this. Okay? Which means that my response for these weak signals will be pretty lame, right? So it will be just kind of Z type. my response for this would be Z-type, and all of this would be my response to a strong symbol, right? Or I can say, no, to hell with it. I really want do something like this. I really want to amplify, like, so most of my dynamic range of responses would go into weak signals, right? This is green. And a little bit for strong signals. I really don't. Okay? So what would you, if you got almighty on day 5, designing a human being, what would you choose? And for which system, by the way? For ear, for example, what would you choose for ear? Ever heard the word decibel? Well, you've been to rock. Well, a rock concert in a closed space is like 100 decibels. What is decibels? You've heard it, right?
It's a log scale of intensity.
It's a log of intensity. Why? Why we measure acoustic intensity in logarithms?
Because we perceive it in logarithms.
Because our ear, here it's a logarithm. This is how our ear works. It amplifies, you're in a forest, you want to hear something which is kind of a little signal. Maybe there is water flowing somewhere, you want to hear it. And you don't want to jump every time that, some kind of, a bear or lion somewhere. You don't want to be that much kind of trouble by this. So, our ear is indeed logarithm, but what would you choose for an eye? By the way, you know why we have two ears, two eyes, right? Why we have two eyes? Depth perception. That we see it's three-dimensional. If we'll have time today, I'll tell you why we see three-dimensional by one eye too. But this is already next thing. This is already active inference. Why we have two ears?
Rotation perception. You can tell.
Oh, yeah, we will have inner ear, which tells us either we are, rolling or we're just on a plane. But basically,
That's not what I meant. I can tell if the sound is coming from here.
direction. Why we have two nostrils?
Redundancy.
You can say about eyes too, it's just redundancy. Incidentally, we perceive 3D by one eye. So why we have two nostrils? By the way, I was given this course several years, and then one girl asked, so why we have two nostrils? And I say, wow, I have no idea. Then I went to physiology and say, not only you. Huh? It's very difficult. It's really, there are smells, but air with which we are dealing is usually turbulent. And it's not a simple diffusion for which you can easily say that the gradient is like here, is larger here. We sometimes, there is coffee, and we go, and indeed, there is coffee there. But two nostrils is that our nose works two things. It smells and it breathes. We also breathe through the nose, right? And those two things which are very, very different, because to breathe, you need a strong flow. And to smell, not necessarily, you want it slower, right? So what my friends in the physiology department told me is that actually our nostrils work in turns. One of them is usually at any given moment having a stronger flow, and another is a weaker flow. Also in a stronger flow, your perception of smell is also a little bit different. There are only big molecules that work this way. So it's pretty complicated things why we have two of this. So it is a redundancy, but it also has a complicated function. Right? Our ear has only one function, more or less. Okay, good. So let's return to the eye. What kind of response function you want for an eye? And again, I remind you that we are now doing not physiology, we are doing information theory, right? So what would you design so that it works? Yes?
I'd go for something like a sigmoidal curve. Or not quite sigmoidal. Sigmoidal would be reflected, I guess. So really sharply upwards, very weak signals. Then
By sigmoid, you mean this?
I'd want it reflected across the XY line. Sorry, so it should shoot up at the
Okay, wait. So you want a sigmoid like this, or you want a sigmoid like that?
Probably.
You got almighty, guys. I mean, switch on your imagination. Yeah. So what you want?
Logarithmic makes sense in general because generally the compared to the uncertainty, like signal to noise, you usually have measurements with an error that is proportional to the signal. So logarithm like kind of optimizes the useful information you get while not picking up noise as much.
You amplify weak signals by logarithms. That's the main property of logarithms, that you amplify weak signals and you dump strong ones. Why would I would need this? Your I, by the way, is a thing which mostly react on a contrast. Right? So just pure white or pure black, we don't give a shit. We're interested in whether there is a white strip on a black or black object moving through the white. Yes? So sigmoid, you say sigmoid. So which one you like more?
I like the latter, but
You like this?
a little bit less flat in the middle.
Huh?
It's ideally like that.
No, I exaggerated, but I mean like this or like that?
The second one.
This one.
The reason being, I want night vision to work nicely, and so you need light to be able to pick up small signals quite well.
Forget it. This is just. You mean that you want it here, and that you mean that you actually aren't interested in medium signals. Essentially, that's what you're saying. But this is kind of something else. This means that you're mostly interested in the medium signals. So in medium signals, you strong react. So here is your medium signals. Here you react strongly on them. Because you react when you change your level of response, right? This means strong reaction. This means strong reaction. That means weak reaction. That means weak reaction. That means strong reaction. Okay.
Yeah, I agree. I guess I'm saying strong reaction to weak signal is important for night vision.
You're doing physiology now, and I'm asking you to do information theory. I say it again. We are doing, from physiological reasons, this could be, because sound is clearly, is kind of a thing which is you really work, because we all know where we live. We live in a world of very many weak sounds and sometimes strong ones. And the strong ones, when we have a police car, blaring somewhere over there, we better switch kind of it off. But when somebody whispers, "I love you," then we really want to hear it with all the details. So this is more physiology, or I don't know, or kind of what signals mean. But now I'm asking you something. I is where we get most of our information, right? Just most of it. And what you want to optimize? It's not sound. It's not our skin which gets a little. It's something which we got 90% of our information through the eye. It's a huge flow of information which flows to it. Okay? So what we would want to optimize here? Something that we learned, right? Because otherwise I won't be asking you and telling that information theory. So what you think is the So now let me tell you the famous work which answered this question. It was Eye of a Fly. There was this signals, and again, how I call it? Just want to keep notations. Okay, so X would be my signals, and then Y would be my sensory. Those are neurons. Well, the first level interneuron, this is I. And so the guy named Laughlin did the following thing. He really made a very good measuring device which measured electrical signals over here. And so he put the poor creature in the lab and changed the optical signal. He immediately recognized that what actually matters is a contrast. So this signal was a contrast in intensity. Now, how much brighter was the next thing? And then he get some response function, namely y is g of x. And it was like this. Okay. Then what he did? He took a camera and went where? Out of the lab. Where he went? Not like Morse in the print shop, right? He went into the lake forest region where this fly actually lives. So he went to a natural habitat of this fly. And what did he measure there? He took a camera. Okay? What did he measure on a lake and in a forest, in a swamp where the fly lives? The camera measures optical signal, right? So what?
Measure intensity, see where it lines up on that graph.
He measured the signal, and the signal was kind of having some kind of a statistics, because, you know, you look there, it's less bright, more bright, less bright, less bright, but you actually measure not intensity, you measure contrast and intensity. Or he was smart enough, he knew how flies actually fly. He did more or less horizontal movement, because flies do not kind of fly, just more or less fly horizontally. So what he found out is the rho of x, right? And then he related g of x to rho of x. How? Now that you know, yes, how?
G of x should be a CDF of rho of x.
G of x?
Should be the cumulative distribution.
Oh, absolutely. So what he found out is that this is g, right, y is g of x. And this is rho okay. So what you find out is that rho is g prime of x, right? With time some constant. But it must be. Why? I mean, if I show you the data, I mean, I really, it's, you know, just look at it. This is the data. So this is experimental data, and this is the theory. No fitting parameters whatsoever. This is Nature 1981. Okay, why? Why actually this function is an integral of this, and this function is a derivative of z. What it tells us about these beings, right? So essentially, if you look at this distribution and, for example, you take an equal things here, right? And then here it would be smaller. Yeah, let me do it in a better form, right? So if you I want to do it on a bigger scale. So you have this distribution, and if you now take a curve of which this is an integral, so this maximum is where this has a maximal derivative, right? And so if you take here equal intervals, like here, it would give you, and if you take here the same interval, it would give you, so the main thing is that because this is equal positions here would mean equal areas here, right? Because this is an, and what it means, this area of it? It's a probability. This is a probability of x. So this interval means the area is a probability of this level of response. This means the probability of this level of response. What essentially Laughlin predicted and measured is that your responses would be equidistant in such a way that you would exploit all your interval of, this is your interval of responses, right? This is y, this is x, with the same frequency. Which means, what about rho of y? So you have rho of x, and you have y, which is g of x, right? So you may say that rho of y dy is rho of x dx, right? You can also say that this is rho of x dx dy dy. This is rho of x 1 over g prime dy, right? Which tells you that rho of y is rho of x divided by g prime of x, right? So now, if you choose g prime, which is proportional to rho, then rho of y is a constant. And what is constant distribution realizes with respect to entropy? Yes?
Maximizes it.
It's a maximum entropy. So in a sense, what was, of course, what you really interesting, you're interested in the capacity of your channel, right? You're interested in the capacity of your channel. It's mutual information between x and y, and it's s of y minus s of y under given x. And Laughlin assumed that this is like 0, namely that your eye accurately sees what is it over there. So whatever contrast you get, this contrast you see, this entropy is 0, which means that it's error-free. So you are maximizing essentially s of y. But it actually works in an even more complicated situation where this is not 0, so your eye can make errors, but it's more or less physiologically fixed. It's not something that is dependent on your statistic of a signal, but the fact is that when you come to a new environment and there are statistics of a signal changes, that the animal, human, insect change the response function after a time accordingly because you maximize capacity. You maximize how much information. Alternatively, you may say that you want to use all your dynamical range. This is your range of signals, wise. You won't use them all with the same frequency. In a sense, it is like what we were doing when we took the letters of an alphabet and a more frequent letter we encode by a shorter thing. This is a more frequent thing. We encode it shorter. If something which is more rare events, we encode it longer. This is the same logic, but now this logic turns into the fact that when you God Almighty and you, on day 5, try to design a response function of an eye, you ask yourself, you create it together with the environment for this being. So if you want to design an eye of a fly, you create lake together with it because it gives you the probability distribution. And when your fly would change the environment, that it would change the way that it encodes the signal. Okay? This is probably first work, and I've decided to tell you, you know, some original works. This is probably one of the first work when somebody took a real data out of the lab and out of the nature, and they were just, you know, no fitting parameters corresponding to the just maximizing entropy of a distribution. So in the new distribution, rho of y is a constant, right? Just a constant, okay? And a little bit more technically, you can say that you, I don't know, you can write it like this. It's your S of y is what? Is an integral of rho of y minus log rho of y dy, right? So then you say that this is minus rho of y dy is rho of x dx, right? And then you take logarithm, and rho of y is rho of x divided by g prime of x. This is what we derive. Now you say that you want ds over dg to be equal to 0, so you look for extremum of this with respect to this function. And of course, when you vary, you obtain that g prime is equal to c rho of x. Okay? But this is a little bit more formal, but essentially you are looking for the extremum of entropy. Generally, our mind works with different types of signal, because when you say what is actually y, what is happening inside, Laughlin assumed that this is just the total current, total number of pulses that neurons say. But a bit later, we started to understand that the signals that neurons send that could be encode information in two different ways. What engineers would say, there is amplitude modulation and frequency modulation. You may say that every spike is just a bit, 1 or 0. And that would be like an ultimate form of amplitude modulation. So that no signal is 0, one signal is 1 bit. But when you look at what actually happens in the neuron, you see that there are a lot of signals, and what also varies is the time intervals between them. It's like frequency modulation. So sometimes you can encode, and apparently brain uses both. So it's not that simple to really, you know, kind of. But in this particular case, when the Laughlin worked with a fly eye, and it really you change contrast, you see what changes in the signal. It's usually kind of go up and down. So there was more or less clear y and clear x in this picture. Okay, this is clear. So the last thing for today is how actually this relation between y and x, how we know what is outside. So the last thing for today is a perception. So how do we know that what we receive is a signal about external world? So how we process sensory information, essentially. So what would be your idea that you've got some acoustic signal or optical signal? What brain does with this signal? What do you think? Try to imagine. Yes?
For acoustic signals, you want to take a Fourier transform. For optical signals, you want to begin by doing edge detection.
So it's also a signal. So you may, then what? What?
Associative memory, I guess.
You mean that you take this signal and what you do with it? Well, I mean, brain is a bunch of neurons, right? Okay. So what it can do is obtain pulses and send pulses. That's what he does. Yes?
Compare it to attributes of memories, to like details copied from memory objects to try to recognize whether it's similar to any of them?
What is memory?
Information stored from.
You mean that there are other? Well, first of all, aren't really sure how it is stored, but the main thing is the following, and this is what I'm trying to, that whatever it does, is it a response to what it received, or it's a function of a response, and like you say, memory, or maybe something else. Imagine that you're a brain. You're a bunch of neurons in a totally black box. Okay? So you grow. You're a bunch of cells. What you get signals, and you send back signals. Okay? Every signal that you get does not carry with it a label like I am from your liver, I am from your ass, I am from your grandmother, etc. You learn it, or whatever, with time. But you actually, the only thing you can do is to send signal back. No other things. Okay? So you get signals, you send signals. A memory is essentially a pattern which appears in your brain on which received signals you send signals back. But one of the most remarkable discoveries, which I, by the way, already mentioned when we were talking about bias framework, is that our brain sends signals all the time without obtaining any input, and at the time of obtaining any input. And already Helmholtz, who started all this, kind of perceived this. You remember I talked to you about binocular rivalry, which already Italians in the 15th century discovered, that our brain sees what it expects. You remember it? Let me remind you that you can make it like this, and you could put dog here and cat here, right? And then you ask what you see. And if you aren't primed, then you sometimes see cat, sometimes see dog. Sometimes you can kind of see this or this. But if you've seen like 5 cats before, you'll never see a dog. Even though a signal is on your retina. Of course, it's there. And moreover, the first neuron, which is right after it just carries the signal over there. Just your brain does not get it because it doesn't want it. Because he already predicted that he will see the cat, so he never sees the dog. So now what I'll tell you is a highly speculative science. Why I'm telling you that it surprisingly finds more and more experimental support, and it's very physical. It's done by physicists. And it took quite a while before biology started playing, but just this year they published a big book, and it's now like everybody talks about it. This book is called Active Inference. It's surprisingly readable. And they spend a lot of time explaining simple things like what is free energy, but you already know what is free energy, so this will be mostly. So essentially, what it tells you that instead of bottom-up approach, namely that you get a signal, your brain processes it, and then come out with a picture of the world, and picture of the world in this particular case is P of X under Y. Let's formalize it, right? That's my sensory input. That's my sensory kind of signal. This outside world, namely optics, I mean light, dog, cat, grandmother. So this is kind of an ultimate thing that you want to get. What you actually have, what your body sets, is P of Y of X. This is just what we discussed, how your eye processed it. For the given X, it gives you that Y. This is right? And this is something which is physiologically determined. But you really need this. This is your picture of outside world under the condition of information that you received by your sensory thing. Imagine that you obtain some Y, a given specific Y. What you guess about outside world? You know this. Your brain knows it from experience. It knows that if you get a kick, that's probably somebody kicked your ass. It's kind of experience which eventually you learn to trust. So one thing is just a maximum likelihood. You say, okay, if I get this y, I need to find x which corresponds to the maximum of p of y under a given x, right? So just find that x which gives you the maximum probability. That would be okay. You say, okay, then x is this. But it's not that what brain needs. A brain needs also confidence in this result. How I am confident that x is like this? And the confidence is essentially distribution, right? Because if you have your p of x under a given y like this is your x naught. This is high confidence. If you get it like this, it still has maximum over here, but this is low confidence. Brain actually interested in this probability distribution. So how you get this out of this? What great formula that we all know you use? You use Bayes formula, absolutely. Let's use Bayes formula. Again, what I'm telling you is highly speculative and yet surprisingly meaningful. And even at the end, I'll say a few words about experimental things. So what you actually write, you write a standard Bayes formula. P of x and y is equal to P of x. That's what you had before, times P of y of x divided on P of y. P of y, just the whole one, okay? And if you just look at this, this is what is called generative model, right? This is something which is essentially P of x times P of y under x. This is just a joint distribution of x and y, right? So this is a holy grail of it. This is your generative model. It tells you how actually the probability of this and this. The answer is how to get it, okay? So essentially, what we are interested in is that before we had this. Now we have this, right? So the change, this is what actually information brought. We know what it is. It's just a relative entropy or mutual information between P of x and y under condition of y and P of x, which was before. And this is, of course, just a mutual information in this case of x and y. And it's not interesting because it's average over all x and y. We are now interested in a particular y, just given sensory input, okay? And then we ask what our brain actually does, how he or she or it changes the perception. There need to be some kind of an algorithm. And first of all, you may take this mutual information, which is the difference between your P of x under given y with a P of x. This is a degree of surprise, right? And what our brain wants with this, it wants it larger or it wants it smaller. Because it'll be trying to build this, right? In a moment we call it Q. It's just kind of some practical measure. So some Q of x for a given y. Y is fixed. What he wanted, large or small? You're a bunch of neurons. You live inside a black box. And what you get, you're getting signal, you're sending signals. Okay? What you try, which brains will be now sending and receiving signals? Those that learn how to survive, right? What survival means? again, we started this lecture from asking how we survive. This is, again, how you survive. Yes?
I guess we want to be able to glean a lot of information from measurement of y, so we want the distance to be large.
We want this difference to be large. You want as much surprise as possible out of information, okay? As this active inference people say, when you fish, you want to stay in water. If you want a surprise, this is the surest way to die. Yes?
Well, I think there's a distinction there because when it comes to seeking information, then maybe yes, you want to get more information that you didn't know, but when it comes to predicting, you want your predictions to be right, so you would want to optimize that part for less surprise.
It's right. So in a sense, because before we were talking about a way of optimizing information flow, then you would naturally may think that you really want to optimize here information flow. But what your really brain actually wants and where he wants to stay. What we are talking about, I want to call your attention to this word, active inference. So we aren't now talking about only getting information. We're talking about survival. Survival means actions. When you get signals, you send signals. Sending signals is an action, right? The brain sends a signal. This signal tells you, look there, move your head, move your arm, right? Don't look there, for example. And essentially, again, this is not a theorem that one can prove, but the idea is that brain tries to minimize the surprise. A fish wants to stay in water. So you want this, but on the other hand, you're also right. It wants its model, its generative model to be as close to reality as possible. So and this is two contradicting requirement. So that on one hand, you want your new probability distribution, your conditional on your sensory input, to be as close to your previous probability. You expect to be in water. X is your environment. You expect to be in water. You really try to interpret whatever happens as that you are still in water. But on the other hand, you need to account as much as possible, which means that you do need to change something. You do need to somehow account for the fact that you get this new information. And as always in physics, as you have two things to balance, when you have two conflicting requirements, what negotiates them is a functional which always have two parts. What is in physics we do when we say that on one hand, our system wants to be ordered because it's nice, because the energy is much lower. But on the other hand, it wants to be disordered because it's nice, its entropy is much higher. And so the quantity which tries to balance and find the true state of a system is free energy. So it's always you try to find something which you want to minimize minus something that you want to maximize, right? And this is a very universal framework. And from now on, this lecture and next lecture and lecture after that, then will be stock markets. They will be doing this. We'll be trying to negotiate two conflicting things by finding the extremum of a functional, and this functional will consist of two parts. Okay. So now let me show you what this brain people do. Most of them are doctors, by the way. They do it for a very, very practical and sometimes even life-saving reasons. So let me write you. So they usually call this Q of X, which means that they will be looking for such Q which finds the extremum of the following free energy. So it's a F, which is a functional of Q of X and function of Y. You understand the difference between functional and function, right? So this is a functional of function and functional of a variables. So it will be D between Q and P of X, right? So this is what you now get after, and that's what you had before, minus sum over all x, Q of X log what you have, P of Y X. Right? This is, let me remind you, this is something which you possess. It's your physiologically given response under a given stimulus, right? So this is something which, in a sense, tells you that you want this minimum, but you want to be as maximally close to your data. So you want your Q to be large where this is large. This is the probability of having this Y, right? So you want this Q to be large where this probability is large for those X. So this is kind of your way to try to be faithful to the data, or we could write it a little bit in more detail, which is sum over X, Q log Q over P minus log of P of Y of X. This is one way of writing. Now I rewrite it. The same thing, I rewrite it differently because there will be three different ways related to three different strategies with which our brain works. So I can also write it as a Q of, again, the sum of a Q of X logarithm Q of X divided by P of X, Y. You see, if I take this log over here, P of X times P of Y of X is just a joint probability of P of X and Y. So I can also rewrite it this, but now I rearrange the things a little bit differently. I take X log Q log Q, which would be minus S of Q, and Q log P over there will be minus sum Q log P of X, Y. And the third way in which I write it, which is yet the third thing, is again the D, but not between Q and P of X. I write now D between Q and P of X and Y, which is ideally what I would really want this. I get this because this is my proxy, right? Okay, but so when I really get it correctly, that would be 0, right? And minus log P of Y. Okay? So when we look at the first line, what it essentially tells us that it's really the degree of change you want it. So you look for a minimum of this functional. Our brain is supposed to look for the minimum of this functional. So you want to minimize the change, but be faithful to the data. You want to maximize as close as possible this quantity. This is the first way. Now, the second line, you can interpret as following. Logarithm of a true probability is type of an energy, right? If you may think about any probability as in a Gibbs form as something like minus E over T. So what you have over here is, let me take it red. So this term is, if your probability is E minus T, so this is essentially E. So it is E minus S. It's a kind of standard form of a free energy telling you that you really want to minimize kind of your whatever energy which is being faithful to the true distribution, but you want to maximize your entropy of Q. This is kind of a second strategy, but it's the same formula. And yet even more revealing is this formula, which tells you that no matter what you do, you're bounded from below by just the probability of your sensory inputs. This is your signals in the brain. They have their own indeterminacy. They have their own entropy. Okay? And here comes the word active. Because you want to minimize this. And there are different strategies. And that's why I wrote all this formula. And these people who really work, and people who work with this, they actually work with the brain data and with types of that people react, etc. And they see that there are different strategies. One strategy is that you can really try to build something which is as close as possible to it. There is another strategy, you say, the hell with it, I would be just maximizing the entropy of it. This is the most effective way to minimize this. But there is yet another way to do it, is to change this. How you change this? This is the probability distribution of your sensory inputs. How you can change this? Well, you can switch the channel, right? You can just look other way. This is why it's active inference. It's not about only guessing information and obtaining it. All our errors in life are here, and also all our discoveries are here, right? Because there is always a way to do nothing to your picture of the world, just nothing. Just switch a channel, look other way, okay? It surprisingly works, because our brain always predicts. And what is the first experimental confirmation of that, as I already mentioned, is that brain always sends signals from the brain to sensory organs. How we distinguish signals which brain sends to the eye and the signals which eye sends to the brain? We do not cut our neurons over there. How we distinguish? Try to guess. So you're experimentalist, right? You send signals from a brain to the eye, but then what comes to the eye is a result of a complicated processing, because what you really get is a degree of surprise, which requires some processing. There are several levels. Your neurons, first generation, second generation, they are complicated. Ganglia, that really do processing. What processing does to signals, it changes frequency. It's a nonlinear operation. When you do nonlinear operation, you change frequency. And so when you measure encephalograms, you see different alpha, beta, gamma waves, etc. So usually you can distinguish that what comes from the brain has lower frequencies than what comes there. So what we do know that when you sit in a dark room and there are totally no visual information, your eye sends nothing back, we see a lot of activity. Your brain always predicts what it expects to see. Okay? And then when it starts seeing something, it compares, it tries to minimize the difference, but not the difference itself. It tries to minimize free energy. One of kind of another confirmation, kind of not direct, is the sheer anatomy of our connection in the brain. For example, there are things related to this Y. They are motorics, right? Like look other way, okay? Like move your hand, do this. Like you don't expect this to be hot, okay? Put your hand in the other place, and it won't be hot, right? This is the way of changing this and staying alive, but. It was noticed that a lot of these things which govern the motorics, they do not connect it to any sensory system. It's also a phenomenon which has a fancy Greek name. I forgot it, frankly, and I didn't even put it into the text because, like all psychologists know this name, and I forgot it every time I learn it. But it tells you that you know your body position without sensory input. Huh? There is some, no, this is something Greek. It could be that there is English analog of it. But it's not only that you can, touch your nose with your closed eyes, but it's also that and you can see it anatomically, that there are a lot of things which are done without any kind of sensory feedback, which is also kind of a qualitative. Maybe one other thing that I mentioned here is that this language, it happened to be, they really kind of try to use it. I don't remember if I told you, they have this problem of deciding where you switch off life support, right? So you need somehow to tell that this brain is in a state of being sentient, right, at having perception, and that other brain is not have any conscience, in a sense. And we may say, well, how you defined it? This is really, there is really one state for which we clearly know what is it to be unconscious. And it's not sleep, it's what? It's the state where you go into this procedure, you come out of it, and there is no memory of any. You wake up in the morning, you know that time passed, right? Which means that you weren't really totally unconscious. But when you go into coma is also such state, but again, we aren't really sure to what, okay, so in a sense we're trying to understand what is coma, but there is also, if you're having a complicated surgery and it's a long one, then they put you under general anesthesia. And this is if somebody were going through it, then you know the feeling. No time passed. Just tuk, tuk. They tell you 3 hours passed, but you're absolutely sure that it was like 1 second. And then you can compare what happens in the brain during this stage, and then you try to compare it with a brain which sleeps, or somebody who is in the coma, but then we try to really say, is this coma is like this general anesthesia, or it's something which is really, because sometimes a brain cannot do any command, but it still perceives. So here it works. What they measure is a mutual information. They found out that in this really, truly unconscious state, the mutual information between different parts of the brain was practically zero. It was orders of magnitude less than the mutual information. So for now, a working definition of what is conscience and how much it is just mutual information between different, actually they take 3 or 4 parts, not only left and right, this is more complicated, but mutual information. So this is now really clinical instrument by which they decide who lives, who dies. It's working already. Italians first who started, Tanoni, I may even write the name. This is, he started it, but there is many other guys. This is already this century. And so what I'm saying is that I'm telling you things which are highly, highly hypothetical at this moment, right? And maybe, I will be alive and teaching this course in 20 years, and many things would change a lot. But I'm telling it to you because it's today's science, right? And it uses the same instruments: free energy, conditional probability, mutual information. That's the language on which they speak. Maybe tomorrow you will be using it in a more sophisticated way, but this is how it works, okay? So it's all for today about brain and mutual information. And it was, I think, the easy part of the course, because next lecture again will be a little bit more formulas, but not that complicated. Questions? Yes?
In the second equation, I'm trying to get an intuition about temperature in this.
Temperature is unity here because everything is dimensionless, right? So kind of my probability is just energy, which means that my energy is also dimensionless. But generally, you are right, because for us temperature, it's what negotiates the balance between entropy and energy. Even dimensionless, that would be next lecture, and then we'll be discussing how self-driving car works, how all the algorithms of perception information. You may change these parameters depending on what you think is more important, right? And it could be that brain really kind of can switch some parameters. Some not, because I intentionally wrote it in the way that when I'm reconnecting, this factor is unity, right? And at the moment, this is, by the way, it's, again, sometimes I'll give you names so that you would recognize. It's Freeston. The first work was some, I don't know, probably 15 were kind of more. But the book is just 2022, this book, Active Inference, for which in the introduction he writes that he wrote almost nothing of this book because it's all based on his work, but some other people try to explain to us. But it's not complicated. It's in terms of formalism, it is this one. When you do the data, it's complicated. So as such, it is with temperature unity. Or in a sense, you already measure energy in bits. Your energy is in bits. Because temperature is a proportionality between ergs and bits. Okay? So now your energy is in bits. Because there's nothing by bits here, right? Energy is things which you want to minimize. Let's put it this way. That, in a way, tells you how to be creative, right? So when you ask what is energy, physicists will tell you it's a generator of time shifts or whatever, or things which is conserved because of time translation invariance and so on. When you ask these people what is energy, say energy is the thing that you minimize, and entropy is the thing that you maximize. You see? This is different approaches. Okay? More questions? Good. See you next week. We're already, 5 lectures?